When we worked out the left-hand endpoint, right-hand endpoint, and midpoint rules for approximating definite integrals, we were approximating the region that is the integral using a shape with a flat top, right? A rectangle that has a flat top. But for most shapes, that's having a flat top seems like a bad idea because, right, most graphs move up and down, and a flat top can't follow the graph as it moves up and down. So there must be a better way. We should be able to come up with some sort of shape that does a better job of following the graph as it moves around. So let's still break this interval from 0 to 2. Remember, the integral that we were looking at was the integral from 0 to 2 of this function, which happens to be sine of x squared dx. And we're still going to have 4 subintervals. So what sort of shape could we use that could follow this curve? Well, how about let's look at the second interval. Having a rectangle, right, with the left-hand endpoints, it would be this tall. With the right-hand endpoints, it would be that tall. Well, now that I have these two line segments drawn, it seems like, well, why don't we just use the trapezoid that joins these two up? So maybe instead of rectangles, we should be using trapezoids. Look at how much better the trapezoid can follow the graph than a rectangle. So on this second interval, we would use this blue trapezoid that I've drawn. On the first interval, I guess we'd use this red trapezoid, which really is a triangle since the left side has length 0. In the third interval, I guess our trapezoid would be something like this. And then on the fourth interval, our trapezoid would be like this. It's a little bit weird to call this a trapezoid, but it'll still work. So all we need to do is come up with a formula for the area of one of these trapezoids. And remember, the area of a trapezoid is the height times the average of its two bases. So I'll call those B1 and B2. And here our trapezoids are kind of on their sides, so maybe I should write it this way. Maybe width times the average of its two heights. That would be a better way to write it. So that's the area of a trapezoid. Remember, we had these x values numbered: x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So the width of each one of these trapezoids is just delta x. Now we need to figure out the heights. So let me write down the rectangle number. Sorry, not rectangle, they're trapezoids. Trapezoid number. So this is trapezoid number 1, this is number 2, number 3, and number 4. And just to take an example, let's look at number 2. So the two heights in this trapezoid are the left-hand side of the trapezoid and the right-hand side of the trapezoid. So we need to come up with some way to express these heights. Well, the height is determined by the function, right? It's this point on the function that determines the left-hand height, and it's this upper right-hand red point on the function that determines the right-hand height. And these two heights are just the value of the function. So it's the function at x sub 1 for the left-hand point, and the function at x sub 2 for the right-hand height. Now comparing the rectangle number to the x's that we have, you see one of them is 1 less than the rectangle number, the trapezoid number, and the other one is equal to the trapezoid number. So the area for trapezoid n is going to be the function at 1 less than the trapezoid number and the function at the trapezoid number. So n, actually I guess I shouldn't have n here, I should have I. So for trapezoid number I, the two heights are f of x sub I minus 1 and f of x sub I. Okay. So what we get when we put all of these together, the total area is, right, the area for trapezoid 1 plus the area for trapezoid 2 plus the area for trapezoid 3 plus the area for trapezoid 4. So this, notice all of these have delta x. So let's factor out the delta x. Also, all of them have a 2. So let's factor out over 2. Okay, so now the area for trapezoid 1, once we've factored out the delta x and the over 2, it's f of x sub 0 plus f of x sub 1. Okay, plus, and now let's write down the pieces we get from the area for trapezoid 2. Well, for trapezoid 2, we get f of x sub 1 plus f of x sub 2. And then for trapezoid 3, we get f of x sub 2 plus f of x sub 3. And then for trapezoid 4, we get f of x sub 3 plus f of x sub 4. And something interesting has happened. So the ones on the end, f of x sub 0 and f of x sub 4, the ones on the end only show up once, right? So here's the first trapezoid, the second trapezoid, the third trapezoid, and the fourth trapezoid. X sub 0 only shows up in the first trapezoid, and x sub 4 only shows up in the fourth trapezoid. But all the other values of the function at x sub 1, 2, and 3, they show up twice. And that's because, right, x sub 1, for example, it shows up in the first and the second trapezoid. So we get 2 times f of x sub 1. And then x sub 2 shows up in 2 trapezoids, the second and the third. So we get plus 2 f of x sub 2. And then by the same token, f of x sub 3 also shows up twice, so 2 times f of x sub 3. All right, so to get trapezoids, we still have a delta x, but a delta x over 2, and the function at our data points, remember these values for the function are typically coming from data points. At the values of the data points, there's sort of a pattern of coefficients. The pattern is 1, and then 2, 2, 2, 2, 2, 2, 2, 2 in the middle, and then 1 at the very end. The way we'd usually write that is f of x sub 0 plus 2 times f of x sub 1, and then plus dot dot dot. This just, the dot 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 kind of indicates that the 2 repeats itself in the middle, and then at the end, 2 times f of x sub n minus 1, and then the very last one, there's no 2, it's just f of x sub n. So this way of approximating the value of an integral, this is called the trapezoid rule. It's a very creative name. So in general, if you need to approximate an integral from a to b of f of x dx using the trapezoid rule, first of all you need to choose a number of subintervals that you want to use, or a number of trapezoids, call that n, and then just calculate this, so often called t for trapezoids, t sub n. Calculate what delta x is. Remember, delta x is just going to be b minus a over 2. So delta x over 2, and then take the value of all of your the value from your data points, and the middle ones get multiplied by 2. It's sort of interesting to note that the trapezoid rule is actually just the average of using left hand and right hand endpoints. So to just actually use this for once, let's approximate the integral from 1 to 3 of 1 over x dx using trapezoids and 4 subintervals. Notice that this integral is one that we could actually calculate exactly. So once we have an approximation using the trapezoid rule, let's compare what that gives us to the exact value just to see how good we do. Of course, usually, if you can compute the exact value, you'll do that. The reason that we're using an approximation method when we could do it exactly is just so that we can compare the approximation to the exact value and see if we're close. Okay, so we need to find delta x. So that's 3 minus 1 over the number of rectangles, which is 4. Right, this is telling us n is 4. So 2 over 4, that's a half. So using trapezoids with 4 trapezoids, we get 1/2 over 2 times, so we need f of x sub 0. And remember, x sub 0, that's the left-hand endpoint. You know, maybe it would help to draw our interval. So we're going from 1 to 3 and breaking this up into 4 subintervals. So the x values are 1, 1.5, so 3 halves, 2, 2.5, which is 5 halves, and 3. So these are our x values, right? X sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. Okay, so f of x sub 0, that is f of 1 plus, remember the middle ones for the trapezoid rule, they all get coefficients of 2. So 2 times f of, we need f of x sub 1 here, and x sub 1 is 3 halves, plus 2 times f of, we need x sub 2, and x sub 2 is 2, plus 2 times f of x sub 3, and x sub 3 is 5 halves, plus, and then the last one doesn't get multiplied by 2. So f of x sub 4, and x sub 4 is 3. Okay, so 1/2 divided by 2 is 1/4. And then this f is the integrand function. So f of x is the function 1 over x. So f of any of these fractions, we just take its reciprocal. So f of 1 is 1, plus 2 times f of 3 halves is 2/3, plus 2 times f of 2 is 1 over 2, plus 2 times 2/5, plus 1/3. Okay. And now we can compute this value. So we could compute the fractions exactly, but since this is a decimal approximation, since this is an approximation of the integral anyway, it seems like having a decimal approximation for the fractional value is probably fine. So let's see. 0.25 times 1 plus 2 times 2/3 plus 1 plus 4/5 plus 1/3. So I get, for some reason my calculator has given this to me as an exact fraction, 67 over 60, which is 1.116, and then just a bunch of 6's after that. Okay, so that's the approximate value that the trapezoid rule gives for this integral. Well, let's calculate this integral exactly. So integral from 1 to 3 of 1 over x dx, that's natural log of x from 1 to 3. So that's natural log of 3 minus natural log of 1. Natural log of 1 is 0. And natural log of 3, if we just punch that into a calculator, natural log of 3 is 1.0986. So comparing these two values, the value from the trapezoid rule and the value of the actual integral, you can see we got pretty close. It looks like we're off by about 0.12, which isn't bad considering the fact that we only used four trapezoids. Right? Usually how the trapezoid rule gets used is you program a computer to do it, and a computer can use 100 rectangles as easily as 4, And so it can use lots and lots of trapezoids, which will give you a very good approximation for the integral. So the fact that we're off by 0.12 is actually pretty good for only using 4 trapezoids.